For small drones to operate autonomously indoors, they need to land precisely on targets like charging stations. But without GPS and with cameras being power-hungry and unreliable in low light, this remains a major challenge. We introduce Moth, a low-cost, bio-inspired system that allows micro-drones to land with under 10 centimeters of error from up to 10 meters away simply by seeking an infrared light source much like a moth to a flame. Moth's hardware is simple, lightweight, and inexpensive. The landing station is just a commercial, off-the-shelf infrared light bulb. To locate the landing station, we use photodiodes on the drone. We implemented and evaluated Moth in two ways, as a lightweight attachment for commercial drones like the DJI Mini 2 and on a custom-designed, palm-sized microdrone. The system uses a two-steps approach for landing. The goal of Stage 1 is to navigate from long range by turning the drone to the correct heading and flying into the proximity of the landing station. Once close, Stage 2 takes over to precisely land the drone using an array of photodiodes. In Stage 1, the drone uses a single motorized photodiode or MPD. It performs a 360-degree sweep, measuring light intensity to find the approximate direction of the landing station. After identifying the direction for peak signal, it turns and navigates towards that heading. In Stage 2, the system uses an array of photodiodes or ARPD. By calculating a weighted sum of the intensity measured by each photodiode, the drone determines a precise movement vector. This allows for the fine-grained adjustments needed for an accurate landing. The closer the drone is to the landing station, the more accurate the method becomes. Let's see a complete end-to-end landing. On the right, we show the RGB video feed and IR video feed of the environment. The drone is controlled autonomously by our algorithm. On the left, this is what Moth's algorithm sees. It starts in the long-range MPD mode, performing a 360-degree scan to find which direction has the biggest reading. Then it switches to ARPD. This plot shows the readings from 6 photodiodes, and the red arrow shows the calculated movement direction based on the weighted sum. The graph on the bottom shows the PD readings over time. This will help us understand when to switch from step 1 to 2. Let's see the demo. After the drone takes off, we start Moth algorithm. It enters Stage 1 first, spinning 360 degrees and use the front-facing PD to measure the light intensity. The light intensities at different headings are plotted on the top left figure. After the scan, it finds and turns to the peak direction and moves forward. This process repeats where the drone would perform measure, spin, and travel again. This goes until now, where during travel, the downward-facing PD readings, blue curve, begin to exceed the front PD readings, orange curve. This is the trigger. The system now switches to the close-range ARPD mode for its final approach. You can see the change to the ARPD vector, making small, precise corrections. The drone uses this information to center itself directly above the IR light bulb and execute a perfect landing. Thank you for watching.